So let's get started today. So I will be going over the test on Tuesday. We're still grading the exam, so I want to know, I'm not going to go over every question on the exam, it would take too long, so I kind of want an idea of where you excelled and where you struggled before I go over the exam, but I will try to get the exam questions and answers posted by tomorrow so you can at least have an idea of what the solutions were. I also had some feedback yesterday that maybe you felt a little pressured trying to finish everything in an hour 15 minutes on the code assessor. And I want to assure you that I knew many of you would not be able to finish. Programming is something where if you get stuck on something, it could take you an hour to find the bug. So it could be that one of you gets it immediately and it takes 5 minutes. For someone else, you'd get it immediately, except for the fact that there's one tiny bug and it would take you an entire hour to figure it out. So the point was that not that you necessarily get through everything perfectly. It was that you would have more time to do it than on a paper exam. If you had a paper exam, all you'd be able to do is try to scribble something down. Okay? Here, with a computer, you could move code around. You didn't have to, if you forgot something, do something like this where you have blah, 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 and then all of a sudden you do blah, 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 and you circle and you do that, and I'm left to interpret what that means. Okay, instead you could just insert that code in there, you can move it around. If you did have extra time, you could start trying to test and debug if you might find that one of my test cases revealed a flaw in your thinking, in which case you could change it. So I've just found it tends to improve the scores. As I said, I didn't expect many of you to finish it. Again, not because you're not capable of doing it, but because even one simple bug could easily take an hour to figure out what is the problem. Okay, so don't sweat it if you didn't finish. The point is not to put pressure on you. The point is just to give you a better opportunity to get a coherent answer together than you could if you were doing this on paper. Okay, and in general, in the past, I've found that the scores are much better when I do it this way than when I try to have one in-class test, because then you're rushing to get through both the paper problems plus the coding problems. Okay, so if you didn't finish everything yesterday, please don't worry. Many of you are in the same boat, and unlike CS 102, we're looking at all the answers and giving partial credit. Okay, so today, what we're doing is finishing up hashing, and I know that most of it is already done. There was just, I wanted to go over the ACM algorithm that Dr. Planck had, so I'll just say the ACM algorithm. And then we're going to get into pointers, which are going to be a fundamental tool that you're going to be using throughout the rest of your CS career. And besides recursion, which we also get to in about a month, pointers and recursion are kind of the two remaining tools that will be in your so-called programming toolkit that you'll be using through the rest of your career. So we'll actually spend 2 lectures on pointers. They take some getting used to, but you'll be seeing them then pretty much through the rest of the curriculum. Okay, so with hashing, remember that there's these 3 basic ideas with hashing. You have a hash table, which is really a vector, and it has a certain size which you want to be prime because it tends to more evenly distribute the numbers. You have a hash function which takes a key and produces hopefully a random number. And you have a collision resolution strategy. And we spent a bunch of time with the collision resolution strategy and with the hash function. We did not spend as much time, with the hash table. We didn't spend as much time with the hash function, and I just realized as I was talking, we didn't really talk a whole lot, if at all, about double hashing, and you had to do that in the lab. So I apologize for that. That's usually not going to happen where we make you do something in the lab which we hadn't talked about in class, and it just slipped my mind, in fact, that we had not done double hashing. So I'll also do that now. But in general, you will not be stuck doing that in lab. And in fact, in the future, if I haven't talked about something in class, no one sent me an email, but feel free to send me an email and say, hey, we haven't talked about this in class. I need some help with it. Okay? Hopefully, most of you still got it. Is that correct, or did most of you struggle with that? Kind of, okay. That's kind of what I expect. Okay. So, the hash function that you used in the labs were different from the two that were, or three that were presented in lecture. But going forward, you're going to find that you tend to use the DJB hash, although Dr. Planck gives it to you. But just to review it, what it essentially was doing was, first of all, you were dealing with strings. Okay, so it's easy to generate a hash function with integers. You essentially just mod it by the table size. It's also easy with doubles because you just round them or truncate them and mod them. So numbers are easy, strings are tougher. And usually what you do with strings is you just think of the string as though it's an array of characters. So, and what you do is you're going to treat the characters as though they were integers, and then you're going to use some function. So here, this is the function that you're using to do your computation. So you set h initially to be 5381, and then at each step, you take the current character and you exclusive OR it with 33 times the previous hash value. So this is just a way of randomizing the characters. So this function here is actually implemented right there. You're simply iterating through each of the characters in the string, and you are supposed to really be exclusive ORing there. So if you remember, bit shifting left by 5 shifts everything in that string 5 bits to the left. So for example, if we had 8 bits, it would shift these 5 bits off. You would no longer have them if you had only 8 bits. These 3 would get shifted 5 to the left, so they would become the leftmost 3, and you would shift 5 zeros into the rightmost position. And that has the effect of multiplying by 2 to the 5th power. We covered this earlier. So 2 to the 5th is 32. So what we're really saying is 32, this is h times 32 plus h, which is 33h. So the less than operator is a very efficient way to multiply by a power of 2. Okay, it turns out that there is also one that goes the opposite way. So I could say h greater than 3, and that's called a right shift operator in this case. What it does is it throws away the lowest 3 bits. So again, if we had 1100, 0010, this right shift throws away these 3 bits. We used to call it the bit bucket. So it throws them into the bit bucket. So these 5 now get shifted over, so they become the rightmost 5 bits, and 3 new bits come in on the left. Okay, So this, if left shifting is equivalent to multiplying by 2 to the I power, what do you think right shifting is equivalent to? Dividing is equivalent to dividing by 2 to the I power. So in this case, this 8-bit integer, if you come up with the number, so that is, let's see, if you want to come up with what it is, there is a 2, there's no 4 or 8, there's no 16, no 32, this is 64, and this is 128. So it's 128 plus 64 plus 2 is what? 194. So if we divide 194 by 8, which is what right shifting by 3 is equivalent to dividing by 2 to the third, at the end of that we should have 194 divided by 8, which is 24, I believe. And if we look over here, we indeed find this is 16 and this is 8, that's 24. So a right shift is equivalent to division, and a left shift is equivalent to multiplication. So questions about that? Okay. So the next one was this ACM algorithm. And if you say, how in the world does someone come up with this? It beats me. Okay, mathematicians spend years coming up with these things. So how he came up with this permutation table beats me. And I'm sure he might have explained it in his article, but I did not read it. So he came up with a permutation table. So right here, these are all unique numbers between 0 and 255. And what he is doing is he is basically breaking something down into these 4 8-byte quantities. Okay, and he is putting that, he's calling that byte hash 4. Okay, so he is basically going to compute his H by, first of all, computing separate values for each of these. So each of these, this might have 3F, this might have 2A, this is all in hex, 1, 1, maybe EF. So these are hexadecimal values. So at the end, once he's computed these quantities, which I haven't told you how to do yet, he is going to perform this operation right here. Okay? This one is bitwise OR. Okay? Remember that the caret is XOR, or bitwise XOR. So that single bar is bitwise OR. What is double bar? OR, Boolean OR. But a single bar is bitwise OR. It says if you have, for example, 1100 and 0110, do bitwise on each of them. So you'd get 110 because 0 plus 0 is 0. 0 ORed with 1 is 1. 1 ORed with 1 is 1. 1 ORed with 0 is 1. Hopefully you learned these truth tables in 130. Okay, so what he's doing is he is by shifting. So he starts with h equals 0. Okay, then he sets h to be h bit shifted left by 8. So what he's doing is he's freeing up 8 lower bits. So initially h is 0, so 0 left shift 8 is still 0. And he ORs that with the first entry. So he has 3f is what h is equal to after the first iteration. Okay, now the second iteration, he left shifts h by 8 bits. So what does that do? It sets h equal to 3f00, because the left shift by 8 bits is introducing 8 zeros at the right-hand side. That's pretty neat, because now when he ORs in J1, notice how that's very cool, because when he ORs it in, it now becomes 3F2A. And then when he again left shifts, he gets 3F2A00. So when he ORs that with entry 2, which is 1, 1, he comes up with 3F2A11. So you see, he's basically just taking these 4 chars and he's putting them together into a single integer, because h is an unsigned int, which is 32 bits. Okay, so he's basically just figuring out a way to put these 4 chars together into a single int. This is the way you do it. And I just realized I was assuming that you had seen unsigned before in 130. Is that legitimate or not? Not. Okay. So unsigned, you did learn about signed numbers in 130, I hope. Okay. So kind of the idea was, I know this is rough, but if there was a 1 in front of it, it tended to make it a negative number, right? And if it was 0, it was positive. If it is unsigned, what it means is that it's treated as a positive number. So even if you have a 1 here, it doesn't matter. It's treated as part of the positive number. So in fact, whereas this might be -1, or I'm not good with 2's complement, so it may not, 1001 may not actually be -1, but I think it is. So if int h was equal to 1001, that would mean h was -1. But if it was an unsigned int, then there's no longer a sign bit. It's considered positive, and now h would be considered equal to 17 because, I'm sorry, would be considered equal to 9, because this would actually be considered part of the number. So unsigned, in effect, gives you 2 things. Unsigned means the number is positive, so there's no sign bit, equals no sign bit, which implies number is always positive. And it gives you 1 additional, it actually doubles the range of numbers. So if you have a signed int, you get -2 to the 32nd to 2 to the 31st minus 1, right? You did learn that. But if it's an unsigned int, now it goes from 0 to 2 to the 32nd minus 1. So you get roughly, you get roughly twice as many numbers, positive numbers with an unsigned int, because you get that extra number at the end, which used to be a signed bit. But in our case, the reason we want unsigned ints is because we just want to treat them as positive numbers. We don't want them to be negative. Okay, so that's why these are declared as unsigned. So the next question is, I explained the code, this code for combining. But the question is, how do you get these 4 8-bit quantities? And that's what this code is meant to do. So what he's doing is starting out and assuming that we have, this is h minus 4, this is h minus 3, this is h minus 2, and this is h minus 1 initially. So these are our pre-hashes. And initially, we're setting them all to be zeros. Okay, so that's this operation right here. It just sets everything to 0. Okay, now what is happening is that at each step I, he is he's using whatever is currently here. So let's say that was currently here was EA, hexadecimal, okay, which is in base 16, I'm sorry, in base 10, that is 10 plus the E is 14 times 16, which is 140 plus 6 times 14, which is 64. 204 plus 10, so that's 214. So what he's doing is he's getting whatever is at location 214 in the permutation table. So let's say that's 155. And he is exclusive ORing it with whatever is the next character in his string. So his string might be smiley. So he's basically just saying that at each step, he is going to take one of these blocks and he's going to exclusive OR it with one of the characters from the string. But first, he's going to take whatever is in this value and he's going to permute it using his permutation table. So it's kind of an extra level. It's his way of randomizing. So the DBJ guy, he randomized by multiplying the previous value by 33. The Pearson person is randomizing by taking whatever the value was, going into this permutation table, and pulling out some random value from it, and then exclusive ORing it with a character from Smiley. So that's what he's doing right here, is byte hash j equals perm table, and then exclusive ORing it with s of I. And then he's incrementing j because each time he's using a different part of a different word from this 4-character table. So initially it was h minus 4, h minus 3, h minus 2, h minus 1. Then it becomes h0, h1, h2, h3, then h4, h5, and so on. So basically, with each I, he's stepping through each of these blocks, and he's further randomizing each of them. So it's just a way of randomizing each of his 4 8-bit quantities. And the hypothesis is that this does a better job of randomizing than multiplying each one by 33 times hi. Okay? So questions about what this is doing. Don't worry about how he came up with his permutation table or his theory. Just the mechanics. Do the mechanics make sense? Okay. So, Dr. Planck did a bake-off to see just how good they were. So he generated, let's see, I think he generated, was it 200,000? No, he generated 100,000 keys, and he produced hashes, and he wanted to know how many unique numbers he got. So he did a bake-off between DJB hash and ACM hash. So he took 100,000 keys and he hashed them. And he wanted to know how many unique hash values he got. So out of 100,000, how many unique hash values were generated? Because this tells him how many entries will be occupied in, say, 100,000 entry hash table. So he found out that 78,605 unique values were generated with DJB hash, and 78,610 were generated with ACM hash. He also checked his first one, remember where we just added up the characters in the string according to their ASCII values, and you can see that that was horrible. It only generated about 2,300 unique values. So what you get out of this is basically DJB hash is pretty much as good as ACM hash. Do we agree with that? Do we really think that a difference of 5 is significant?
It's just one test.
Pardon?
It's just one test, though.
That is that true or not?
Maybe he did it multiple times.
I think he did it a bunch of times. I'm not 100% sure.
I know it says on the next one he read it like 10 times.
That's me, actually.
Oh.
So sometimes I add to his notes.
Okay.
So while I said I, sometimes I means Dr. Planck, and sometimes I actually means me. So actually I was curious because, so I looked at that and thought, okay, I actually don't know whether that's good or bad. Because the true test of how good they are is if you just take 100,000 random, if you just generate 100,000 random numbers, you'll get some collisions, right? So the true test of how good it is to generate 100,000 truly random numbers and see how many of those were unique. And then I did run it 10 times because I knew the objection could come up, well, it was only run one test. So I did it, and it turns out that I only got 78,742 distinct ones by doing 100,000 random numbers, which means that both DJB hash and ACM hash are pretty darn good. They're almost as good as a random number generator. Okay? So they're both very good. And which one is more complicated? The second one. So why would we ever use it? I hate to say it, but God bless him, Pearson spent a lot of time coming up with a really sophisticated hash function that works no better than a much simpler one. So in practice, speed is everything. And since speed is everything with a hash function, we just use the simple one. I love it when simple is better. This isn't always the case that simple is better, but in this case, simple is better. So we use DJB hash. Now, he did torture you in the lab by making you do XOR and last 7. He did that because he wanted you to get experience doing hash functions. Yes, Zach?
Could it be the case that under one hash function, collisions are predictable, and then under another hash function, they're not so predictable, so even though they may have the same...
Yes, they would be predictable in the sense that maybe one generates a longer chain that is true. So we didn't actually check to see. It is the case that out of the, so it's possible, that's a good point. It's possible that even though each of them came up with the roughly the same number, it may be, I don't think this happened, it may be that 20,000 keys in DJB hashed to one location and the other 80,000 were pretty much unique, whereas in ACM hash, of the ones that collided, only 2 ever collided into one spot. So it's possible. But given this performance, highly doubtful. Okay? I would not want to take the side of the bet that said that DJB hash actually produced worse so-called dispersion than ACM hash. I bet they produced essentially the same dispersion. By dispersion, I mean good collision behavior.
If you're using something like PGP key,
You may want to know the distinction, yes. But I'm willing to bet he's not doing any better. And this isn't a statistics class, so once you get to 313, ask your 313 instructor, okay? But at any rate, the point is DJB hash seems to be pretty good. Okay, now, let's see. Did that. Okay, the other thing that unfortunately we had not talked a lot about was double hashing. So double hashing, you should know, is never used in practice. So I shouldn't say that. Almost never used in practice, which is why I skimmed over it. Okay, has the best theoretical property or theoretical performance of any open addressing scheme. So it's better theoretically than linear probing or quadratic probing. So why, despite having so-called better theoretical performance, is it not used? The reason is that computationally it's more expensive. So 1, 2, sorry, going over here, 3, double hashing is computationally more expensive. More expensive than linear or quadratic probing. Because you have to compute 2 hash functions. And computing 2 hash functions is time consuming. So in practice, we don't use double hashing, even though in theory, it leads to the fewest number of probes. Remember in lab 4, Dr. Planck asked you to calculate the total number of probes for find. So double hashing minimizes double probe or total probes. It will do better than quadratic probing and better than linear probing. Unfortunately, the problem is that maybe with total probes, quadratic probing, each probe might, let's say, this is just theoretical, but this is what it comes down to. Let's say that each probe takes X time. And with double hashing, let's say its total probes takes 1.75 X time. So when I say that double hashing is theoretically has better performance, what I mean is that quadratic total probes is greater than double hashing total probes. So theoretically, double hashing is better. But the problem is each probe in double hashing takes 1.75 times more time than in quadratic probing. So unless the number of total probes is significantly less than the number of quadratic total probes, double hashing will be more expensive. And in fact, double hashing doesn't give you significantly fewer total probes. That's the problem. It gives you a few fewer total probes, but the few total, it's like if this is 100, this might be 90. So the 90 times 1.75 is greater than 100 times 1. So it turns out in practice, double hashing isn't as good. I just went through a lot of math in 3 minutes. So I'm going to take questions, starting with Gavin.
So why does it take so much longer if you just need to calculate one other hash value?
Okay, so the reason, we haven't gone into it yet, but, so actually, think about what you did in lab 4. So double hashing, you had 2 hash functions, right? One was XOR and one was last 7. So to do double hashing, it was h of I was equal to h of key plus I times f of key, where f was your second function. Okay? So whereas quadratic probing, this was double hashing. Quadratic probing was h of I equals h of key plus I times I, right? So it comes down to this has to be computed with double hashing. Okay? Whereas this is free for quadratic probing. The problem is, so if you used last 7 here, you had to calculate XOR here. So if this in effect took, say, 5 nanoseconds, probably this is also going to take about 5 nanoseconds, right? So, whereas this takes 5 nanoseconds, and this is free, so this is 0 nanoseconds. Now this multiplication is going to take something as well. So let's say the multiplication takes 1 nanosecond in each case. So overall, quadratic probing took 6 nanoseconds and double hashing took 11 nanoseconds. Okay, which if I divide 11 by 6, I come out close to 1.75. That's the problem. So that second hash function that you compute is almost as expensive as the original hash function. Whereas with quadratic probing, the second value was for free. So in fact, double hashing is really closer to 2 times rather than 1.75 times. I was being generous when I said this was 1.75. This was really closer to 2. And it's not getting a 50% savings in total probes, not even close. So it loses in the real world. So one of my favorite sayings is, there's nothing more sad in history as beautiful as the murder of a beautiful theory by a gang of ugly facts. So the idea being mathematicians and academicians come up with lots of beautiful theories that look great in the lab, but when you try them in the real world, they get brutalized by inconvenient facts, or as Al Gore said, inconvenient truths. So in theory, double hashing is great because it reduces the number of total probes. But in practice, doing the second computation isn't free, and that murders the performance of double hashing, thus making quadratic probing the heavyweight champion of the world. So quadratic probing wins in practice. But are there any other questions about the math that I kind of took you through? Yes.
Well, isn't part of it also like if you wouldn't want to optimize for probes since probes are much cheaper than computations on a computer?
But they aren't. The probes turn out to be cheaper than the computation.
That's what I'm saying. Like you wouldn't want to optimize for probes.
Right.
Yeah.
That's right. So that's why I'm saying double hashing loses. Because double hashing optimizes for probes, but probes are cheaper than the computation, so quadratic probing wins because it's only a little less efficient than double hashing on total probes, but it's computationally much faster. That's why I just said quadratic probing is the heavyweight champion of the world.
Yeah, no, I mean, like, why would they optimize for probes in the first place?
Because mathematicians love to do this. Because it's fun to be able to claim that you came up with the theoretically, if all computation was free, which it's not, it's fun to be able to claim that you came up with the best theoretical performance.
Computer scientists, though, most mathematicians aren't worried about hash tables.
Right, true. There's a lot of things that are done in academics that don't pan out in the real world, okay? So I must present this to you because it is apparently occasionally used, but I'm just telling you that in practice, no one uses double hashing. However, you must know it as computer science students, okay? So at any rate, that is the idea, is that double hashing, going way back to right here, that's what it's doing, is it's h of key plus I times f of key. And that's what you did in lab 4. So for example, let's say that our, let's see, again, we start by doing our insertions into this hash table. So we first insert Luther, Binky, and Rosalita, and we're going to assume that they get put in locations 1, 2, and 4. Now we try to insert D'Antonio, and D'Antonio's hash value is that. Okay? So D'Antonio collides with Luther. So we calculate H2 using ACM hash, and that equals this value right here, which mod 10 is 9. So what we do is we keep adding 9 to the original hash value, and in this case that gives us 9 plus essentially 1 is 10, and we put D'Antonio in location 0. Okay, now with Frenchie, we get this one, which collides with Binky. So we calculate H2 of Frenchie, which is this. We get 7. So when we add 7 to this number, we get, in effect, 9 when we mod it with 10, and Frenchie goes into location 9. Okay, and so on and so forth. And the idea is that when you do h of key plus I times f of key, since this is a random number, supposedly, whereas with quadratic probing, I times I is not a random number, this gets better dispersion than this, because f is a random number. So that's why, theoretically, double hashing works better. It gets better dispersion because f of key is a random number. However, if they did the theoretical performance and look just, if you can, at quadratic probing versus double hashing. L is the load factor. Does anyone remember what the load factor is? Right, the number of keys in your table divided by the table size. So it's how full your table is. So the bigger L is, the worse the performance of open addressing. But how bad does it get? Okay, if you look there, how bad, much worse on an insert is quadratic probing than double hashing? Come on, you all can do subtraction. It's only 1/2 probe worse. Okay? For unsuccessful searches, it is 1/2 probe worse. And for successful searches, it is actually gets to be, that's the one point where double hashing can be significantly better than quadratic probing. Okay, but you tend to keep your load factors around 0.5. So this happens to be about 2. Okay, times whatever this is. And it turns out that between your inserts and your unsuccessful searches, that this one kind of blemish on quadratic probing isn't enough to overcome the fact that it's only 1/2 probe worse for unsuccessful searches and insertions. So in practice, quadratic probing works out good. Now, if you look at linear probing versus, say, quadratic probing, this factor right here is a killer for linear probing. Because that, let's say the load factor is 0.8. 1 divided by 1 minus 0.8 is 5. Okay, it's 1 over 0.2. 1 over 1 minus 0.8 squared is equal to 1 over 0.2 squared, which is 1 over 0.04, which is 25. So linear probing tends to be quadratically worse than quadratic probing. So quadratic probing is a big improvement on linear probing. And if you look at this, the big winner is separate chaining. So in the real world, unless memory is an issue, we use separate chaining, which is why for the rest of this semester, you will only see separate chaining. Separate chaining is easier to implement and in practice is the fastest, but it uses more memory. So if memory is an issue, like in a smartphone, maybe you would use quadratic probing instead. But if memory's not an issue, separate chaining is what we use in the real world. Questions? We good? Okay. Deep breath. We're moving on. And we're moving on to something called pointers. So, you kind of learned about memory, hopefully in 130. Remember that in the real world, when you have like int A and int B, they are really stored at memory addresses. Okay, and this is hexadecimal. So really, A and B are stored at memory addresses. Hopefully you also remember from 130 that you used to do things like load memory addresses into registers, right? You might say load register 0 with A, which was really load register 0 with the address. Well, no, that actually really was a load of register 0 with the contents of A, but it really was load register 0 with 0x1000 is how that got translated in machine language. So you were really loading from memory addresses. Okay, so in a high-level language, we talk about variables like A and B, but at the assembly language, or machine language, we are talking about memory addresses. Well, it turns out that sometimes we want to be able to use memory addresses in a high-level language like C++, because originally C was designed for operating systems, and it was important that you be able to refer to memory addresses. So what we'd like to be able to do is actually sometimes have a variable like C, which instead of having a value, actually has a memory address. So in this case, we say that C points to A, hence a pointer. So to declare that something is a pointer to something else, we put an asterisk in front of it in the declaration. So the asterisk says that C is a pointer. So C is called a pointer variable. And instead of storing an integer, it is storing an address to an integer variable. So we say that C is a pointer to an integer variable. So in the case that I have, the example I have up here, what is C a pointer to? Which variable? A, because it's storing the memory address of A. So what a pointer variable does, a pointer variable stores the memory address, the memory address of another variable. And it has to be a variable of the appropriate type. So in this case, because I declared C to be a pointer to an integer variable, it must store the memory address of an integer variable. It should not be storing the memory address of a string variable, for example. Okay? So we call it pointing because you can kind of think of C as pointing to A. Okay? So how do we use pointer variables? First of all, how do we make, if we have int A and we have int star C, how can we make C point to A? The way we make C point to A is with the ampersand operator. That's supposed to be an ampersand, sorry. I don't make them too well. So that says the ampersand returns the memory address of A. So gives memory address of A. So instead of giving me the value, the integer value stored at A, the ampersand gives the memory address of A. So now C contains whatever the memory address is of A. Okay, let's say that we wanted to use C to change A. Okay, so if we say star C equals 20, what we're really saying is that A equals 20. So when we say asterisk C, this is called the dereferencing operator. And what it says that instead of storing 20 in C, it says store the right-hand side value. So RHS is my shorthand for right-hand side value into the variable pointed to by C. So if I say C equals, we assign the right-hand side value to C. But if we say star C equals, we store the right-hand side value into the variable pointed to by C. Does that make sense? This is the fundamental thing of pointers. If you can remember this, you will be able to build on this. Okay? So let's go actually to Dr. Planck's exam. His midterm one. And work through his example. So he says, tell me the output of the following program. Okay? So let's just do the top part right now, this part right here. Okay? And I am going to tell you, let's see, actually, he should have, but he didn't. Did he not? Ah, he did not. Doesn't matter. See if you can't figure out what is printed by these three cout statements. So take a moment, look at this. Based on what I just told you, see if you can figure out, I did not tell you one thing. So before you try to figure it out, there's one more thing. Let's say that I have int A and B and int star C. So I say A equals 30. So this is what I have here. A, B, and C. So I store 30 into A. Now I say C equals ampersand A. So C is equal to what? 0x1000. Now I say B equals star C. Based on what I told you about this, what do you think this statement is doing? Saying what? You're good, Gavin.
Assigning A to B.
It's assigning whatever variable C points to B. And since C points to A, it's actually assigning the value of A, which is 30, to B. So when it's on the right-hand side, this is saying assign or retrieve the value stored by the variable to which C points. So the dereferencing, if it's on the right hand, if C is on the right-hand side, it says retrieve the value stored by the variable to which C points. If, on the other hand, it's on the left-hand side, it says store the value on the right-hand side into the variable to which C points. Okay? Are we good with that? Now let's give the exam a try. Okay, feel free to talk with your neighbor. I'll give you about 3 to 4 minutes for this. It might help for you to actually draw a little table like I did. You actually don't need to know the address of A, but if you really want, if it makes it easier for you, we'll just say this. So how many of you need more time? Okay, sounds like we're there. Okay, so what do we think the value of A is? What gets printed by Cout for A? 32, very good. What gets printed for B? 22 is good. And what gets printed for star C? 32. So if you don't see that, here's what happens. This statement sets A to be 22. This statement makes C point to A. Specifically, it gives it the memory address 1000. So C now points to A. This says take the value of the variable to which C points and assign it to B. Well, C points to A. A is the value 22, so we assign 22 to B. This statement, you should remember, just like I'll get to you, adds 10 to A, giving me 32. So the Cout statement, A is 32, B is 22. Star C says, give me the value of the variable to which C points. C points to A, so we print 32. Yes?
In the Cout statement for C, if you remove the star,
Mm-hmm.
would it throw an error or would it print 0x1000?
It would print, I think, it should print 0x1000. It should know it's a pointer. Let's give it a try. So, whoops. It's either going to give you 0x whatever the memory address is in base 10 or in hex. So I want to see whether Cout does it in hex. It's one or the other. It's either going to be in base 10 or hex. So now, first of all, it's not going to be put at location 0x1000. So don't expect it to be 0x1000. Oh, so fun. Yep, there it is, an incredibly long number. Actually, from this, you know how many bit processor my machine is. Am I running a 32-bit processor or a 64-bit processor? 64 bits, because there are 16 hexadecimal digits there. So I'm actually running a 64-bit processor. That's a 64-bit memory address. Okay. Any other questions about that? Okay. So, looking at Dr. Planck's notes for a moment. Actually not. Looking at my notes, there's one other thing. I said extend page. So let's say I had int d, and after I said all this, I say d equals c. What do you think d is equal to now? So d is a pointer variable and c is a pointer variable. Okay, so c's, okay, so we have two possibilities here. I've heard both. One is that d could contain c's memory address. So one possibility is that d contains 1008. The other possibility is that it contains 0x1000, which is the memory address of A. So it does point, right, so you're right, Ashley. No matter what, it's going to point to a memory address. The question is, does the memory address it contain, is it going to be 1008 or is it going to be 1000? Okay, it is 1000. If I put an ampersand there, that would have given me the memory address. Don't worry if you missed it. This is why I did it. If I put the ampersand in front of it, it would have been 1008. That would have given me the memory address. But because I did not put the ampersand in front of it, it gave me the contents of C, and the contents of C are 1000. Okay? Don't worry if you missed that. The reason you said 1000, Ashley.
No, I said 1,000.
Oh, you said 1008? Okay.
But it's a. What if you set D equal to B?
If I tried to set
Without an ampersand?
D equal to B without an ampersand is a great question. It would give me, should give me an error message saying that the types are incompatible because it's not an address. It will say, it should, the compiler should say incompatible variable types error. Let's see if it does, okay? That's what it should do. Let's see if it does. So let's go ahead and assign, we're going to set C equal to B here. And there we go. There's your message, Ashley. Assigning to int star from incompatible type int. So it's unhappy about it. So it says, in fact, what to do about it. It says take the address with ampersand. So it's actually telling you how to fix it. Yes, Zach?
How does it know what is a legitimate address?
Because it looks at the declarations. So it looks at the fact that, so it looked at here where you said D equals B, it looked at B and says you declared B as an int, and you declared D as an int star, and those aren't the same. And it hollers. Okay. So this illegal. This is legal because D and C are both int stars. So it makes C and D now, in essence, both point to A. Okay? So, let's see if okay, so Dr. Planck is big on these pointers. That's fine, but I also want you to understand that what's really happening is that the pointer variables have these memory addresses rather than integer values or char values. They have memory addresses, and that they do point to a variable. So it's fine to think of it this way, but know that internally it's really a memory address. Okay? Now, you should all be okay with all of this. Okay, one last concept for today. It turns out that pointers are going to be useful because some of the data structures that hash tables we were able to do using a vector. But we're going to start getting into other types of structures like lists. And lists are going to require this pointer variables because they're going to point to each other. Okay? So the next thing we have to talk about is that we sometimes want to be able to create new objects at runtime. And the way that we do that is by using something called the new operator. So let's say that I have int star a, and I say a equals new int. That's different than before. Before, I was doing this. I was saying a equals the address of x. Now I'm doing something different. I'm saying a equals new int. What this is doing is saying, in essence, allocate a new, I'll say, unnamed variable that is an int, and return its memory address. So this variable has no name, okay? And it's allocated from a different pool of memory. So I don't know if you covered this in 130 or not. So there are two types of memory in a program. There's what is called stack memory, and there's what is called heap memory. Were you introduced to the notion of heap memory in 130? No. Okay. So, when you execute a function, so if I have a function like int add, int x, int y, what happens is it creates a stack frame for add that has memory for x and y, and main also has a stack frame. There is a second type of memory called heap memory, which is what this new operator goes to in order to allocate memory. So in this case, I'm asking for a new unnamed variable that is an int. So it goes to the heap, and it gets some memory from here, like say from 0x5000. So in this case, a would equal 0x5000. We say it's getting memory off of the heap rather than from the stack. Okay, so we say that this is in effect creating new memory at runtime. And this is going to take some getting used to. Okay, so it's like an unnamed variable. It has no name. It's coming out of the heap, and I'm able to address it only through this pointer. So if I say star a equals 100, it will assign the value 100 to this unnamed variable. Okay, so this is where Dr. Planck here is starting up. He has int I. Okay, so there's I. And then he has int IP and IP2. And the first thing he does is he makes IP point to I. So that's what gets us this first pointer. So he's saying that IP has the memory address of I, so maybe 0x1000. Then he sets I to 5, so there we go. Now, he says IP equals new int. IP1 equals new int. In fact, Dr. Planck had a bug here. He should have said IP1. We'll fix that. So now he says IP1 equals new int. So this is a totally new piece of memory that is allocated right here, and IP1 points to it. So now if we say star IP1 equals 10, we say 10 is stored into this new piece of memory. I'll take about 1 or 2 more minutes and I'll be done. Okay, now we call it again down here. So for a second time, we call IP equals new int. So this maybe gets us memory at 0x5004. So now it points to 0x5004, and nothing points to 0x5000. And so we say that our program has a memory leak because this piece of memory can no longer be accessed. Because it was a so-called unnamed variable, it has no name. The only way it could be accessed is if something pointed to it. So we have to be careful to clean up after ourselves if we are no longer pointing to an unnamed part of memory. So we'll get into that next time, which is how we manage memory. With pointers, we're now going to have to start managing memory. That has been done for us automatically in the past, but we will have to henceforth do some memory management. So we will discuss that next Tuesday. Also next Tuesday, we will finish Dr. Planck's exam problem, and we will get into more complicated pointers that point to objects of classes.